Welcome to pre-class lecture 24 on bifurcations and chaos. When we talk about a bifurcation, we're talking about the qualitative change in the behavior of a system, an ODE system, due to changes in the parameters of that system. So we're going to see some examples, and in particular, we're going to look at a saddle node, a transcritical, a pitchfork, and a hop bifurcation. How do we do a bifurcation analysis? This is all part of the dynamical systems analysis that we've been learning so far, but this time we've got parameters involved. So for every analysis, as we've always done, our first step is to find all the fixed points, and along with that is finding their stability. Now remember, in one dimension, we found stability by looking at x versus dx dt plots, and in 2 dimensions and higher, we need to look at the eigenvalues of the associated linear system. When the system is nonlinear, we are looking at the Jacobians. Now, when there is a parameter in the model that can change in value, it turns out that the existence and the stability of those equilibrium points you have found can change. And so the next step in this analysis is to determine where those parameter-dependent changes happen. Where these changes happen are called bifurcation points. The term bifurcation has not been around for a very long time. It was first introduced by Henri Poincaré in 1885. And along with this concept of the importance of where and when bifurcations take place was the development of bifurcation diagrams, which we are going to get some practice creating. A bifurcation diagram is a useful way of getting a big picture overview visually of what is happening to the nature of the equilibrium points as a parameter changes. Now, in the examples we're going to look at, the saddle node example we're going to look at in 1D, but you'll get a chance to do a 2D example in class. Similarly, for transcritical, we'll look at 1D, pitchfork, 1D, but for a hop bifurcation, we need to look in at least 2 dimensions, and we'll get a chance to practice this in class as well. Let's go to the next page to start our examples. A saddle node bifurcation is the first of the examples we're going to look at. This is a case where the parameter changes and 2 equilibrium points that are already in the system are going to move to meet and then collide and vanish. Alternately, 2 equilibrium points could show up out of the blue. Because of being able to show up out of the blue, these are often called blue sky bifurcations. Now, as we look at our example, it's important to identify what our state variables are and what our parameters are. In this case, we have one state variable in a one-dimensional example, which is x, and we have one parameter r. The ODE is dx dt equals r plus x squared. Now, how do we find the fixed points? To find the fixed points, we set x prime to 0, which means that we are going to need x squared to equal minus r, or x to be plus minus root minus r. Clearly, we're already seeing that whether a fixed point exists, whether a real fixed point exists, is going to depend on the sign of r. Now, as we've done before, a useful way to understand the stability of the fixed points is to look at an x versus dx dt plot. Remember, when we are plotting dx dt, we are plotting the right-hand side, r plus x squared in this case, which is a quadratic. Let's first look at the case r negative. When r is negative, the square root will exist, and the function looks something like this. Now, that function intersects the x-axis at the points plus root r and minus root r. The next question to ask is, which of these points is stable and which of these equilibrium points is unstable? We know we can see this clearly because where the curve falls below the x-axis, the derivative is negative and the solution is moving left. We indicate this with leftward moving arrows. Now, on the other hand, for x less than minus root r or greater than positive root r, our derivative is going to be positive, so our solution moves right. We indicate with rightward moving arrows. Now, if we look at the left-hand fixed point minus root r, we see that all solution trajectories are moving toward minus root r, making minus root r a stable equilibrium point. On the other hand, when you look at the right-hand fixed point positive root r, all solution trajectories are moving away from positive root r, making positive root r an unstable equilibrium point. Okay, that's the case for r negative. Let's move r to the right and see what happens when r is 0. When r is 0, our parabola just touches the origin and then comes back up again. So in this case, we only have one equilibrium point right at the point x equals 0. What direction are the solution trajectories moving now? Well, on the entire curve, our derivative is positive, so solution trajectories are always moving to the right, which we'll indicate by placing rightward moving arrows on the x-axis. What does this tell us about the single equilibrium point 0? It tells us that it is semi-stable, which we'll indicate by coloring in half the circle on the left side where it's stable, and the other half will stay open on the right side where it is unstable. This means, of course, that if our initial condition starts negative, it's going to move right and get stuck at 0. On the other hand, if our initial condition starts as a positive value, it's going to keep moving to the right and head off to infinity. Let's look at the final case when r is positive. In this case, our parabola has no real roots. Our derivative is always positive, but there is no place for it to go except to always move right, no matter what our initial conditions are. So in summary, what we have seen, in the case r negative, we actually have two real roots, one of which is stable and one which is unstable. In the case that r is 0, we have exactly one real root, one real fixed point, and that happens to be semi-stable. In the case r is positive, there are no fixed points at all. So how do we tell that story using a bifurcation diagram? A bifurcation diagram is a plot that generally has the value of the bifurcation parameter, in this case r, along the x-axis, and the position of the equilibrium point on the y-axis. Now we know that for r positive, there are no fixed points, so there's nothing to plot. For r equals 0, we do have one fixed point, and for r negative, we have two fixed points, one of which equals the square root of minus r, and one of which equals the negative square root of minus r. Now, the shape of those plots will look something like this. So this is a start, but there's actually a little bit more information that we can include on this. For example, whether or not that fixed point is stable. So remember, if we look back at the r negative case, we see that the negative root r equilibrium point is stable, whereas the positive root r equilibrium point is unstable. We indicate that by using a dotted line for the unstable branch and a solid line for the stable branch. This is the bifurcation diagram for our particular ordinary differential equation system. Now we can see from the shape of that diagram why it is called a blue sky or a saddle node bifurcation. This exactly fits the description of two equilibrium points colliding as r moves to the right and then vanishing. Let's go to the next page. Here we'll see an example of a transcritical bifurcation. In this case, a fixed point that exists is not just jumping into existence or disappearing. It exists for all values of that parameter, but as the parameter changes in value, that point is going to exchange its stability with another fixed point. The logistic equation, by the way, is an example of an equation that has a transcritical bifurcation. So our example is going to be a normalized logistic growth example. We identify our state variable x and our parameter r. The differential equation is x times r minus x. Once again, we can do an analysis of the location and stability of the equilibrium points by plotting the x versus dx dt plots. We also see through an algebraic analysis that there are going to be only two fixed points, and those are going to be x equals 0 and x equals r. In the same way we did with the previous analysis, let's plot the x versus dx dt functions. Now we have a downward facing parabola, and I can anticipate that there will again be three cases, one for r negative, one for r equals 0, and one for r positive. Now remember, we always have two fixed points, x equals 0 and x equals r. So I know there will be a fixed point at 0 in each one of these cases. And of course, through each of these, I can plot the right-hand side of the ODE. You see that as r grows from negative to positive, we go from a downward-facing parabola with two fixed points, then it slides through the r equals 0 point, and then back up to having two more fixed points as the whole parabola moves to the right. With these plots, we can now again analyze the stability of each one of these fixed points, using whether or not the derivative dx dt is negative or positive. When r is negative, there will be a second fixed point for negative r. When r is 0, there will only be one fixed point, r is 0, x is 0. And for r positive, there will be a fixed point at positive x equals r. Take a second yourself to pause the video and figure out the stability characteristics of each of these fixed points. Okay, everywhere the function is negative, we can draw leftward moving arrows. And of course, for the case r equals 0, the arrows are always moving left. And everywhere the function is positive, we draw rightward moving arrows. Looking first at the r negative case, we can see that the left-hand equilibrium point is unstable since all trajectories are moving away from it, whereas the right-hand equilibrium point 0 is stable. All trajectories are moving toward it. As r moves to the right and r becomes 0, we see that coming in from the right, trajectories are going to get trapped at r. However, from the left, trajectories are moving away, so that's a semi-stable point. And r equals 0 is also a bifurcation point. For r greater than 0, what do we see? The right-hand equilibrium point is still stable, but now the stable point has positive value and continues to move right as r increases. Whereas the point 0 has lost its stability when r passed through it. It's like r stole the stability from the origin and ran away off to the right with it. So what are we seeing in summary? There will always be two fixed points. When r is less than 0, which if we're looking at logistic growth is actually not going to be physical, x equals 0 is stable, so that means no population, and x equals r, which is a negative number, is going to be unstable. Right at the point that r is equal to 0, those two fixed points merge into one fixed point at 0, which is semi-stable. And finally, when r becomes positive, x equals 0 becomes unstable, and the population is going to want to move toward x equals r, our stable equilibrium point. So what is a bifurcation diagram going to look like in this case? Again, we plot parameter r against the location of the equilibrium point. And what we see is there will always be two equilibrium points, 0 and r. So one equilibrium point is always along the r axis, but the stability switches. And one equilibrium point, x equals r, will always exist. But remember that 0 is stable when r is negative, and x equals r becomes stable when r is positive. So we draw solid lines for those. On the other hand, x equals r is unstable when r is negative, and x equals 0 becomes unstable when r is positive. So we draw a dotted line for those. This is a bifurcation diagram for a transcritical bifurcation where stability between two fixed points swaps as a parameter changes in value. Let's go to the next page. Here we see an example of a pitchfork bifurcation in which the system transitions from having only one fixed point to suddenly having three fixed points. So you can imagine that the shape of the bifurcation diagram essentially looks like a pitchfork, which is why it gets that name. Our example ODE in this case is going to be rx minus x cubed, and we can carry out the same kind of analysis that we've done in the past. When we solve algebraically for fixed points, we see that since we have a cubic, we have potentially three fixed points. X equals 0 and x equals plus minus root r. As before, we only have real roots when r is positive. Remember, there's nothing wrong with having complex roots. It's simply that we cannot plot them on the phase portrait. Once again, knowing that the nature of the fixed point set is going to be different when r is negative and when r is positive, we are going to use plots of the x versus dx dt function in order to determine the stability of the fixed points. In the case r negative, we have a cubic with only one real root at 0. In the case r equals 0, we still have a cubic with one real root at 0, which has become slightly flattened. And finally, in the case r positive, we have a cubic with three real roots. Let's identify everywhere that our solution is moving to the right. That is everywhere where the derivative is positive, and then everywhere the solution is moving to the left, everywhere the derivative is negative. Now it's straightforward, once again, to identify the stability properties of the fixed points in each of these cases. When r is negative, we have one real fixed point at 0, and it is stable. R equals 0 is a bifurcation point and is still stable in this case. And then for r greater than 0, we have three different cases. The left-hand equilibrium point is stable. The right-hand equilibrium point is stable. And 0, 0 has lost its stability and become unstable. Let's take a look at what the bifurcation diagram is going to look like in this case. Here we have our cases summarized. There's one fixed point for negative r that is stable. At 0, we have a bifurcation point. And for r positive, we have two fixed points that are stable, and 0 has become unstable. So for r negative, we have one fixed point, and it is at 0. So we simply color in the 0 axis, and we leave it as a solid line since it is stable. Now for r greater than 0, we actually have three equilibrium points. We have 0, the r-axis, and we have plus and minus root r. Now, since plus and minus root r is stable, we will leave those as solid lines. But since 0 is unstable, we are going to make it a broken line. This is our bifurcation diagram for a pitchfork bifurcation. It turns out there are a couple of kinds of pitchfork bifurcations. This one is called a supercritical pitchfork. And the reason is that the outer equilibrium points are stable. A subcritical pitchfork bifurcation, on the other hand, would be one in which the outer equilibrium points are unstable. And it might look something like this. Let's go to the next page. The last kind of bifurcation I would like to share with you is known as a Hopf bifurcation. This one requires that we work in 2 dimensions or higher in order to see it. Why is that? It is because what happens in this case is the stability of an equilibrium point is going to switch, and suddenly a periodic solution appears, such as a periodic limit cycle. Examples in biology that exhibit Hopf bifurcations include the predator-prey model we've looked at, Hodgkin-Huxley action potential, a Selkov model of glycolysis, and the Brusselator that you're going to be working on your homework. And of course, there are many more. The appearance of these periodic solutions is of interest to people because this represents a cycling in nature that we can see naturally, and we want to know for what parameters will this kind of cycling arise. The example we're going to look at here is based on a simplified model of glycolysis that was developed and published in the European Journal of Biochemistry in 1968. This model actually has 2 parameters in it, but one of them we're going to fix at the value 0.1. Our state variables are going to be x and y, and the bifurcation parameter we're going to be looking at is alpha, and we're going to allow that to lie between 0 and 1. Now, the analysis in this case is going to be slightly more complicated than what we've done in one dimension because we are going to have to understand the stability in terms of a Jacobian, which means that we're going to identify the right-hand side here as f1, function of x and y, and the right-hand side of dy dt as f2, function of x and y. And on the right there, I've simply rewritten the right-hand side. It turns out there's always going to be one fixed point in the region in which we're looking. And we're going to see how, as alpha ranges between 0 and 1, a limit cycle is going to appear and then disappear. But first, let's find the location of that fixed point by first finding the x and y null lines. Pause the video and see if you can find the x and y null lines and where they intersect, which will be where the equilibrium point is. Looking at the x and y null lines, we can see that the null lines are going to cross when x equals alpha. And when x equals alpha, that tells us what y is. So we see that the system has one equilibrium point that depends on alpha, and at alpha equals 0, that equilibrium point is at the origin. Now, it turns out that because of the nature of these equations, it's not super easy to solve explicitly for the location of the bifurcation points, but we can do some numerics and we can look at sample alpha values for which the stability of our equilibrium point is different. So in order to understand the stability, we have to look at the Jacobian at different values of alpha. Again, we're fixing b to be 1/10, and we allow alpha to range between 0 and 1. Pause the video briefly and write down the general form of the Jacobian for this system. Here's the general Jacobian. Now let's determine the stability of our equilibrium point at 3 different values for alpha. Let's try alpha 0, alpha 1/2, and alpha 1. I'll leave it to you to confirm that the y equilibrium point value for each of these values of alpha is in fact what I've written down. Now, even though these are only going to be 2x2 matrices, if it turns out that you're dealing with obnoxious fractions in the entries, it is okay to use some sort of online calculator for what the eigenvalues should be, because our goal here is to get a sense for what kind of stability we have. So we may do that in this case. We'll see. We probably don't need it for 0, 0, but we may need it for the other two. So let's try looking at the stability property of the point 0, 0 when alpha equals 0. Take a moment, work out what the Jacobian is at 0, 0, and see if you can figure out what kind of equilibrium point and what stability 0, 0 has in this case. Since we have two real and negative eigenvalues, this means that 0, 0 is a stable node. I'm going to open up a second page so I can do the computations for the Jacobian at the other 2 points without having to squish my writing too much. Let's now evaluate the Jacobian for alpha equal 1/2. This is one of those cases where the entries are some obnoxious fractions, and so I'm going to use MATLAB to determine the eigenvalues of this 2x2 matrix. Okay, these are ugly, but the point is that we have a complex set of eigenvalues with positive real part. That means that our equilibrium point has now become an unstable spiral. The other thing that's happening that I'm not going to take the time to show you analytically, but I will show you numerically, is that this unstable spiral is actually converging toward a stable limit cycle. That means that somewhere between the stable node and the unstable spiral, a Hopf bifurcation has taken place. Finally, let's look at the Jacobian for alpha equals 1. Again, obnoxious fractions, so I'm going to use MATLAB to find the eigenvalues. What does this tell us? We once again have complex eigenvalues, but now the real part has become negative. This means that our point has regained its stability and has become a stable spiral. Since there was once again a change in stability and the disappearance of a limit cycle between alpha equal 1/2 and alpha equals 1, there was another Hopf bifurcation. So in this case, what is our bifurcation diagram going to look like? Now that we're in 2 dimensions, we have to decide whether we want to plot the x equilibrium point or the y equilibrium point, or whether we want to plot both of them. Whether we plot one or the other or both just depends on the information that we want. Let's start with the x equilibrium point. Remember, we're only looking at alpha between 0 and 1, and we know that the x equilibrium is simply equal to alpha. So all we do is draw a straight line. So what information can we get from this? Well, we know that there is a loss and regain of stability. And so that is what we will identify on this bifurcation diagram. We know that up to some point that happens before alpha equals 1/2, we have stability. And we know that after some point for alpha between 1/2 and 1, we have stability. And somewhere in between, stability has been lost. So we indicate the lost stability with a dotted line. Now, the question is, for what values of alpha is this happening? And again, this is something that is better worked out numerically in this particular case, but I can tell you numerically that this will happen approximately around alpha being 0.42 and alpha 0.78. By the way, this map is not to scale. If I were to plot the bifurcation diagram in alpha and the y equilibrium, I wouldn't really get a whole lot more information, except I would see the shape of the y equilibrium as a function of alpha. And it turns out that shape is something like this, which again, we're going to see numerically. And again, not to scale, but around 0.42, stability of the equilibrium point is lost, and around 0.78, stability is regained. So we again identify the stable region with a solid line at the location of the y equilibrium, wherever the y equilibrium is stable as a function of alpha, and with a dotted line wherever the y equilibrium is unstable as a function of alpha. Let's go to the next page to look at some example snapshots of the face portraits. These face portraits were created with software called Auto Portrait, which runs in Mathematica, and I will put a copy on our class Canvas site for you if you want to play with it. It's pretty useful. The differential equations that we are modeling, again, are the Selkov glycolysis equations. The number of equations is put in here with a slider. The differential equations are typed in here on this left-hand box, and the ranges and starting values of the parameters are typed into the right-hand box. In this case, we are always setting our parameter b to be 0.1, and we're looking at the case alpha equals 0, where our equilibrium point is at the origin. Now here we can see a plot both of the phase portrait, and we can also see a plot of the solutions over time here on the right. First, notice with these time solutions that the trajectories are moving very quickly in x and y toward a stable equilibrium. And let's see how that looks in the phase portrait. In the phase portrait, we see that my equilibrium point here is at 0, 0, and all trajectories are moving toward it. The other thing I want to point out is that the nullclines here are plotted in purple. Which one do you think is the x nullcline and which one is the y nullcline? Take a look at this picture, look at the direction of flow, and see if you can make a good guess. Okay, noting that the flow through this curve always tends to be vertical, that indicates that it must be the x nullcline because there's no left-right movement. For b equal 0.1, the y nullcline almost looks flat. It's not quite flat, but it looks pretty flat, and it is this here, where there is only left-right movement. So it's clear here that for alpha equals 0, our equilibrium point 0, 0 is a stable node, just as we predicted with our Jacobian. Let's look at the alpha equal 1/2 case. Here, our equilibrium point is 1/2 10/7. And I've plotted two different cases where our solution trajectory starts outside the limit cycle and inside the limit cycle close to our equilibrium point. So you can see first that with the time plots, in both cases, the solution is clearly approaching a stable limit cycle, and we see that through these stable oscillations. For our phase portraits, for the left one, I've started my initial condition outside the limit cycle, and for the right one, the initial condition is inside the limit cycle. I did this so that we could see very clearly how our equilibrium point has lost its stability. When you start very close to the equilibrium point, which is the red dot there in the center, your solution trajectory is going to spiral away from it. So we clearly have an unstable spiral. But we also clearly see a stable limit cycle because all trajectories in both of these phase portraits are attracted to that limit cycle. So our analysis that we did with the Jacobian is in fact confirmed numerically, and we see that equilibrium point 1/2 10/7 is an unstable spiral. Finally, let's look at the case alpha equals 1. Our equilibrium point is at 1 10/11, and we can see, looking at the time solutions, that there are oscillations shrinking to a constant, meaning we've got a stable spiral. Looking more closely at our phase portrait, we see clearly now that our equilibrium point is in fact drawing all trajectories toward it, and it is in fact a stable spiral. So our equilibrium point 1 10/11 at the value alpha equals 1 is a stable spiral as we predicted. Okay, in class, you are going to get a chance to analyze differential equations that exhibit these different kinds of bifurcations, figure out what they are, and plot the bifurcation diagrams. And we're also going to talk a little bit about chaos. So see you in class.